Okay, let's start Lesson 3, Intersections and Segments. We're going to go a little bit deeper into segments than we did on the last time. So, start off with, what is a real-life intersection? So I want you to sit and discuss with somebody what you think a real-life intersection might be. Okay, whenever I think of a real-life intersection, I think first off of, like a four-way stop on the road. Here's your two streets. Right here, you have an intersection. Or you could think about in a school, in our school, if there's two hallways, this right here is an intersection of the two hallways. So, a formal definition of an intersection is the point or points that two or more figures have in common. Now we mostly see it represented like earlier, where you have two lines, and right here there's an intersection. They both cross at this same point here. And it doesn't just have to be two lines. You can have two segments. You could have a segment and array. Just so long as that there is one place that both of these meet. That's an intersection. Okay. Now we have two postulates. For postulate 3, what I want you to do is look at this picture and just try to come up with something to conclude what's going on with what you know about intersections for postulate 3. So pause the video and just kind of contemplate about what's going on. Okay, so what I hope you came up with is looking and seeing that there are two lines, but what do these two lines do? They intersect, and where do they intersect at? Right here. What this postulate says is that if two lines intersect, then their intersection is a point. So if we have two lines that intersect, their intersection is a point. Now I want you to look over at postulate 4. Here we have two planes that are intersecting. So I want you to pause the video and kind of think about what's going on here, what's created when these two planes intersect. Okay. Now, from what we know about planes, they're a bit different. They're bigger than lines. They have a bigger dimension. So it's probably not going to be just one point. You see all these dots here kind of gave it away. It's a lot of points. And it's not just a lot of separate points. It's a lot of separate points together. What this postulate says is that if we have an intersection of two planes, they intersect to form a line. So if two planes intersect, then their intersection is a line. Now let's talk about distance and length. Here we have point A, and over here we have point B. We have two different points. Well, what's the distance between them? What's the best way to find the distance? Would we do something like this? Probably not. That's not the fastest way because we went up and down. The fastest way from point A to point B is a straight line. And when we draw that straight line, we also form a segment. Now this segment has a distance or a length. Let's just call it 4. And when we write this, we're going to write it as AB equals 4. Now you notice that the AB looks kind of like the segment part without the little thing on top. Whenever you write a distance or a length, you don't write the little figure above the letters. And this will only work really for segments. You can't find the distance of a line or array because they go on forever. So we know that AB equals 4. Now, I just use distance and length interchangeably, but they aren't always interchangeable. I want you to pause the video and think about what's the difference between a distance and a length. Okay, so they are very similar, but they are a bit different. Distance can be an exact measure. We can say the distance from A to B is 4. But a distance can also be estimated. You can estimate a distance. You can say that looks 4 miles away. That looks 20 yards away. With length, it has to be exact. We have to say the length of AB equals 4. We can't see the length maybe 4. Length has to be exact. So distance can be exact or estimated. Length has to be exact. Okay. One more postulate. Postulate 5. Segment addition. Now here I have a segment AB and a segment BC. Now I'm going to say that AB equals 2, and let's say that BC equals 4. So this is 2, this is 4. What does AC equal? I want you to think about that by pausing the video. Come up with your answer, but not just come up with the numerical answer. Come up with, why does that work? Okay. So we see that AC equals 6. We can see that AC equals 2 plus 4, which is 6. The distance from A to C is 6. But to do that, you actually had to use this postulate called segment addition. Nowhere in this example did we say that AC was 6. We knew that from here to here was a distance, from here to here was a distance. So what you did in your mind was you put those two together to get the whole thing. So what you did was you said that AB plus BC equals AC, which is true. 2 plus 4 equals 6. Now let's talk about congruence. Congruence happens if you have two figures or objects and they have the same shape and size. And the symbol for congruence is this right here. It's like an equal sign with a squiggly line above it. Now there are certain things we can't really say are congruent, like a line. Because does a line have size? Can you measure a line and say it's this many units or this many feet? No. But we can talk about segments. So let's say I have a segment right here that's 3. We'll call it AB. So I have another segment over here that's also 3. We'll call it YZ. What you can say now is that AB is congruent, segment AB, is congruent to segment YZ. Whenever you put congruence, you're going to use the actual symbol for the figure. So a segment is congruent to a segment. At the same time, we can also say that the length of AB is equal to the length of YZ. So if we have an equal sign, we don't put the figure. So congruence, they have to have the same shape and same size. Now segments have the same shape, they're just a line from one point to another. And if they have the same size, it means that they're the same length.